All right, stop talking, please. Hi, everybody. What I'd like to do is to kind of pick up where we left off in Chapter 10. So again, Chapter 10, we're talking about probability. Last time we had talked about, yes? Sure. We had talked about how to calculate the probability for combined events and for mutually exclusive events. So for combined events, we have oops.
Is it dependent events?
That's independent. We haven't. That's where we left off. That was just a note for me. I'm just reviewing what we had done before. So we have combined events that we can find via this. And as like a special case of this, if we have those two events are mutually exclusive, this formula simplifies down, because what does mutually exclusive means? It means that the intersection is empty. So we have the minus A intersect B just kind of drops off. So this is the two big takeaways from last time formula-wise. Today, what we're going to start with is the idea of independent events. So let's say that we are playing a game where I flip a coin and you try to guess whether it's heads or tails. Okay? The last 10 flips have all come up tails. What are you guys going to guess this time?
Heads.
Why do you think that?
Because it has to come up.
You're all wrong.
So because it's always heads, tails.
Nope. So the odds of it coming up heads or tails is still 50-50. Flipping a coin is an independent event. The previous outcomes of the flip have no effect on the future outcomes of the flip. So just because I've gotten heads or tails 10 times in a row doesn't make it more likely for heads or tails to come up this time. It's still 50-50. Is everybody okay with that idea?
Yeah.
That's something called like the gambler's fallacy, is where you assume dependence when there is none. So like again, you'll see people at the casino, you're too young to go there probably, but playing like a game like roulette, where you see like the last 10 spins, the ball landed on a red spot, so people start betting heavily on black, assuming that, oh, the black, it's due to come up black next. It's not any more likely to come up black now than it was the previous 9 spins. So, for example, tossing a coin is an independent event. We'll look at in a moment some examples of things that would be dependent events, where the previous outcome does affect the future outcomes. But flipping a coin, what it came up before, doesn't matter what's going to happen next time. So the nice thing about independent events is that they are multiplicative. So if I want to find out the probability of tossing a coin and getting heads, and then tossing that coin again and getting heads a second time, we can use this formula. So the probability of heads and then heads is the probability of getting heads times the probability of getting heads. So 1/2 times 1/2, or 1/4. Does this same thing hold true for a dependent event? the second probability will change for a dependent event. So let's just get a quick example of a dependent event. Let's say we are drawing cards from a deck, and we want the probability of getting two hearts in a row. So the probability of getting a heart and a heart. The probability of getting the first heart is 13 out of 52, because there's 13 hearts in a deck of cards. But if I've already pulled out one heart from the deck, how many hearts are left in the deck? 12. And how many cards are left in the deck? 51. And I'm too lazy to do that multiplication, but you guys see the idea here of a dependent event. So here, the probability, or the outcome of the first action affects the probability of the second action. Is everybody okay with that idea? Okay. Yes, Sydney? When it's a, do I ever use the, oh sure, but notice that this formula is for a union, and right now we're talking about how to calculate intersections. Does that's what you're curious about? Yeah, so it's a different tool to look for a different probability. And we'll get, after we get through this, we'll do some real life examples and help sort through how you know which formula to use in which sort of situation. Okay? I just want to kind of hammer through. Okay. So the next section is about using tree diagrams and Venn diagrams. These tree diagrams that we're going to look at are going to be heavily applicable in the next section as well. So we're going to do some examples here to just kind of show you how I can build a tree diagram and how I would use it. So we have, let's say we have a bag of marbles, and we have 5 reds and 3 blues. And let's say that we have, we pick a marble and then put it back and then draw another marble. And let's say that we want to look at the following probabilities. Say we want the probability of getting a red and then a red, the probability of getting a red and then a blue, the probability of getting a blue then a red, and the probability of getting a blue and a blue. So let's see what can happen. So in our first draw, what are the 2 possible outcomes? Well, I could get a red marble, or I could get a blue marble. Everybody okay with that? The probability of getting a red is going to be 5 out of 8, because there's 5 red marbles and 8 total. And the probability of getting a blue is 3 out of 8. Now we'll draw our second The second draw, again, I could get a red marble, or I could get a blue marble. Probably getting a red is still 5 out of 8. Why is it still 5 out of 8? We're told that we're putting that marble back after we draw it. Very good. And then if we draw the blue first, you could get this.
I don't know how many draws.
It says pick a marble, put it back, and then draw another. So that's 2.
Oh, maybe you can do how is the first draw? How come the first draw is 1 and 1 2 diagrams and 1 is 2?
Because if I've drawn a red, 2 things could happen. Or if I drew a blue, 2 things could happen. So let's do this for a moment. Let's do this probability, and maybe you'll see how we're going to use this tree diagram.
Okay.
So if I do want the probability of red and red, I've drawn red for the first part, and then I draw red for the second one. Everybody agree with that? Is drawing these marbles an independent event?
Yeah,
Because we're putting the thing back. So this really becomes the probability of red times the probability of a red, or 5/8 times 5/8. Everybody okay there? The probability of drawing a blue and then a red. Oops, I did the other order. I did red and then a blue. So again, the first one we picked was a red, and then the next one we picked was a blue. So we've gone that path. Again, as Zach has said, since we're putting the marbles back, these are independent events. So I can do just the probability of drawing a red times the probability of drawing a blue. Now let's do the next one, which is the probability of a blue then a red. So here, this time I'm going to go down the blue path, and then the red path. So the probability of blue times the probability of red, which is 3/8, and then 5/8. And then my last one is the probability of a blue then a blue, which is equal to the probability of blue times the probability of blue, which is this path. Sydney? Well, here's where it gets a little bit tricky, is because in this question we've implied that the order mattered. What if we tweak this problem a little bit, make it a little bit more complicated, and you'll see why the tree diagram is going to become very useful for us. And this is venturing closer into what we would be doing in section 7, but we can modify this problem a little bit if you're like, I still don't understand why I need this stupid tree diagram. So let's suppose we have the same 5 red marbles, 3 blue. We draw 1 marble and then another. Notice what we're not doing here. We're not putting it back. Okay? and we want the probability of 2 reds, the probability of red or blue, and then the probability of 2 blues. So I'm going to redraw my diagram. It's going to look just like the one before, but the probabilities will change here on the second step. So we have 5 out of 8, 3 out of 8. And now, what's the probability of getting that second red one? How many reds are left? 4, because we've taken one out. And how many marbles are left? 7. Now what if we do the blue then? How many blues are there? No. What did we take out here? We took a red out. So there's still 3 blues, but there are only 7 marbles.
This is on the first probability of getting 2 reds and a blue. Is that why? Is that how you know?
How I know what?
Like, is that how you know you don't expect blue?
Well, it's because what did we take out on that first draw on this path? I took the red out. Yep. So if I look at the second path, what have I taken out on my first draw? The blue, right? So how many reds are left? Still 5. And how many total marbles still are there? And how many blues are left? Sean. And still 7 total marbles. Shh. That bug's not going to harm you.
Oh, I hate bugs. Oh my gosh. No.
So this is, I drew a blue, and then I drew a second blue. So if we want to do the probability of 2 blues, is there any other way to get blue other than that path? No, right? So it's going to be 3/8 times 2 7s. Likewise, the probability of 2 reds, there's only one way to get the 2 reds, right? It's that path. But if I want the probability of getting a red or a blue, how many different ways can I do that? Well, I could draw the red first and then a blue second. Or I could draw the blue first and the red second. That's a bad 5. Yes, Olivia? Well, here the order doesn't matter because we're not told that. We're just saying if you have a red one or a blue one. It doesn't say red then blue. Well, because you don't have a red marble and a blue marble or a blue marble. Well, this is an independent event, so red and they're mutually exclusive. Like you can't draw a marble that's both red and blue. So the probability of red and blue is 0. Right? So there is no way to, that's impossible. Does that make sense? Let's do another example of kind of using the tree diagram. So this is from page 313, example 10.9. So it says, if the weather is fine, Mr. Liu walks to work. The probability that he is late is if it rains, Mr. Liu rides the bus. And the probability that he is late is 0.3. The probability of rain is 0.45. So let's draw a tree diagram for this situation. So what is this situation dependent on? The weather, right? So if the weather's fine, one thing happens. If it rains, another thing happens, correct? So my first split is going to be no rain, and then rain. Everybody okay with that idea? What's the probability that it rains? Yeah. And so the probability that it doesn't rain then is? Everybody happy with that? Now, if it rains, now what's the second thing we care about here? I guess I should say that. Yes, we care about lateness. So if we had no rain, we are either not late or we are late. If there was no rain and we walked, what's the probability that Mr. Liu's late? 0.1. And the probability he's not late then is? 0.9. Okay. If it does rain, again, we have the probability that we're not late and the probability that we are late. What's the probability that we are late if it's raining? And the probability that we're not late then is? Thanks as well. Everybody okay with how we've constructed our tree diagram? And now I might ask, what's the probability that Mr. Liu is late? So I see two paths to getting late, right? I could end up late going down that path or end up late down that path. Is everybody okay with that idea? So there's two different ways we could end up being late. So to get the first path, 55 or 0.55 chance of it raining, and then, or not raining, and then 0.1 chance that we're late, or 0.45 chance of it raining, and a 0.3 chance of us being late. Which is a different question than, say, probability that we walk to work and are late. So what's that probability going to be? We walk when it doesn't rain, and then we're just being late. So that would be 0.55 times 0.1 on a 10. Is this feeling a little bit better in terms of kind of how the vocab of what they're asking really becomes important? I can't stress how much, like, reading comprehension, I know as stupid as that sounds, but it becomes really kind of an important skill in kind of decoding some of these story problems. And we'll do some more examples of using these tree diagrams when we get to talking about probabilities with replacement and without and conditional probabilities that happen a little bit later. Let's do an example where we use a Venn diagram now, as we've done a couple of examples using trees. So this is from page 316. And this is example 1010. So it says we have 95 students in the IB program. We have 45 of them study biology. 39 study French. 24 study bio and French. So this, to me, sounds like a Venn diagram situation. So what part of my Venn diagram do I start filling in first? The intersection, good. So I have 24 that do both biology and French. So how many people study just biology then? I have 45 total, but 24 of them we've already placed, so we have 21 that do just biology. How many study just French? 15. And how many don't take either of those two classes? How many total should we have? How many have we placed here?
59. That's 45 plus 15.
That's 39. Plus 21 more is 60. Correct? So there must be 35 outside. Everybody agree with this? So the probability we study bio or French is going to be, well, here we could use the combined events formula. So we could say the probability of bio plus the probability of French minus the probability of bio and French, since OR is the same thing as union, right? So if I did that, I'd have 45 out of 95 plus 39 out of 95 minus 24 out of 95. So when I do that, I get 60, nope, Yeah, I get 60 out of 95, right? Is everybody okay with that? Or you could just think of these as mutually exclusive. So if I do that, I would do 21 out of 95 plus 24 out of 95 plus 15 out of 95, and I'd still get 60 out of 95. So why am I able to do with the mutually exclusive? What did I do separately here? I considered only the non-overlapping parts that involved biology or French. So I treated these as, oops. Oh, come on. Ah! So I treated these things as 3 disjoint or non-overlapping sets. Everybody's okay with that? Versus when we looked at the combined events, here we had everything overlapped, so we had to be a little bit more careful, right? When I did the bio and then I did the French, I double counted that intersection, so I had to make sure I subtracted that off once. So either way of approaching it is fine, and the Venn diagram provides you like enough flexibility that you can do that rather easily. So what if I wanted the probability that we don't study bio? So one way you could do this is you could think about it as a complement. So not bio is the same thing as 1 minus the probability of bio, which is 45 out of 95. So I get 50 out of 95 when I do that subtraction. Or the other is you could do it as like mutually exclusive events. So you could say, okay, we have this one. Wanted a highlighter, please. And this one that are not in the bio circle. Everybody agree with that? So you could also do it as like 15 out of 95 plus 35 out of 95. And we get that same 50 out of 95. So either way of thinking about it is fine. Again, one of them, the advantage is you don't need the picture if we just did it as a combined events problem or just as a complement problem. I didn't really use the Venn diagram to do anything. But if you think about it as a mutual exclusive problem, that's when we used the Venn diagram, and it was kind of critical to us getting our answer. Is everybody okay with doing this? And again, I want to try to talk about the different ways that you could think about this, or the different ways you could do these, because very much these simple probability problems that we're doing here can be attacked a variety of different ways. We've done kind of without and with replacement problems already, right? When we did the marble problem earlier. So I'm just going to reference see the marbles example earlier. And we'll go up to 10. So a conditional probability we write in this form. So we draw this vertical line here. And what this means is it's the probability that A occurs given that B has already occurred. And the formula that we'll use to do this is the following. So it's the probability of A intersect B divided by the probability of B. So that's going to be our key for a conditional probability. So let's hear what a conditional probability question kind of sounds like. So this is from page 323, example 10.11. Okay, so Zoe has a drawer with 5 pink socks and 7 blue socks. Zoe's weird because she has not an even number of socks. Without looking, she draws one sock and puts it on, and then draws a second sock and puts that one on. So what I would do for this is I would start by drawing a tree diagram of this situation. So for my first draw, what could happen? I could get a pink sock, or I could get a blue sock. The probability of getting a pink sock is 5 out of 12, and the probability of getting a blue sock is 7 out of 12. For my second draw, if I drew a pink sock, I could draw a second pink sock, but the probability there now is 4 out of 11. Why is that 4 out of 11? Because we've already taken one pink sock out. Or I could pick a blue sock. The probability there is going to be 7 out of 11. We haven't taken any blue socks out, but we have taken a pink sock out. Everybody still okay with what I'm doing here? Similarly, we have this. So this will be our tool that we'll use to do this. Oh, thank you. Because I messed up. Appreciate that, Maddie. Let's find the probability that Zoe draws matching socks. What are the ways that Zoe could draw matching socks? Well, you could have a pink and then a pink, or you could have a blue and then a blue. Everybody agree with that? So pink and pink is 5 out of 12, 4 out of 11. And then plus blue is 7 out of 12, 6 out of 11. So that was just a probability with or without replacement, or without replacement problem. What a conditional probability problem sounds like is, given that she picks 2 socks that are the same color, let's just say picks a matching pair. What is the probability that they are blue? So the cue to me that this is a conditional probability problem is this phrase, given that, or suppose, or something kind of in that word choice. Tells you that something has to happen. So we want the probability that we have blue given that we have a pair. Everybody okay there? So if I use my conditional probability problem, that is the probability of blue and a pair divided by the probability that we have a pair. Everybody okay with that idea? So the probability that I'm blue, that I have a blue pair, was that. And the probability that we have a pair was this whole thing. And I think that actually finishes chapter 10. Amazing timing on my part.